All right, my friends, welcome. So, my name is Filip, and this is a session that I think is probably a bit unusual for an event like this, because it is a session in which we are not going to learn anything useful. So, let me just go quickly and remove all the red cards. So on that bombshell, we can begin. Now, so the idea is as follows. We are actually going to explore the true nature of reality. And if you think about this, asking what is reality or how reality works, in a way, it's sort of the most fundamental question that you can ask as a human being or as a thinking being. So from that perspective, I hope that this is going to work out. So the plan for today is as follows. We will have a look at several experiments from the field of quantum physics, and we are going to experience them firsthand. Now, we are not in a physics lab, so we will not be able to do those experiments here. But instead, we will use a skill that we all have, and that is software development. And the software developers, we are actually used to modeling things in code. We are used to thinking about problems in code. We are used to grasping new concepts by looking at the code. And so we'll try to reconstruct those experiments using a quantum programming language called Q#, and then we'll be able to run them and sort of reason about what is happening there. And so hopefully it works out. And there's actually a reading list that goes with this session if you're interested. Because as we progress, we are going to be sitting at the intersection of quantum computing, quantum physics, and the philosophy of all of this, right? And so from each of those areas, I'd like to recommend a book. Now, I have to admit, so the quantum computing book, that's actually mine, and there are much better books on this subject that you could get. But it is my session, right? But the other two I can actually recommend wholeheartedly. So there you go. Now, this is the company that I work for, and I work in R&D. If you are familiar with the Microsoft MVP program, I'm actually an MVP for or in the quantum category. So not many people know that such category even exists. And this is the motto for today, and I apologize for quoting a Danish person, but it's a wonderful quote from Niels Bohr, right? Everything that we call real is made of things that themselves cannot be possibly regarded as real. And we will see that actually there is some merit to what Bohr is saying here. So let's start very briefly with just a tiny historical background. So when we think about quantum physics, we go back to year 1900, because this is a year in which Max Planck introduced the concept of quanta. So quanta, that's singular, and then quantum, that's plural. And at that time, it was purely a mathematical trick. So basically, he was working on the so-called black body radiation problem. And in order to have the experimental data fit the theory and the equations that he was working with, he could no longer treat energy as this sort of continuous thing, but actually, he had to consider that the energy is actually emitted in discrete packets, and that was what he introduced, right? He didn't realize the significance of all of this, but that actually started a revolution. Now, over the next 25 years, scientists tried to model an atom, and Niels Bohr was the first one to partially succeed. He won the Nobel Prize for that. But actually, as it turned out, it was not possible to model the behavior of electrons within an atom using the classical equations of motion. So it only works for the super basic cases. And such a model was inherently unstable. And the breakthrough came in year 1925. In fact, almost exactly 100 years ago, because it was in July 1925, when Werner Heisenberg published this paper that we see here in the background. He was very young at the time. I think he was 23. And basically what Heisenberg did was a very radical step. He abandoned classical equations of motion, and he introduced the concept of observables. So basically, he decided that it is not worth pursuing, modeling the behavior of electrons within an atom when we are not looking at them, and we should just be focusing on what happens when we are observing them. And this is a very radical, or this was a very radical step, but it's really at the heart of how quantum mechanics works, and we will see this in action as we go forward. Now, quantum mechanics is the foundation of all quantum physics, and actually has been tremendously successful, right? Because just about anything that you associate with this sort of highly developed high-tech civilized world that we live in is really only possible because of our ability to master quantum mechanics, right? So it has propelled humanity on this unprecedented growth path over the past 100 years. Without quantum mechanics, there would be no superconductors, no semiconductors, no transistors, no chips, no lasers, no GPS, no computers, no wireless communication, no MRI scanners. Just about anything that you think of as being high-tech is really only there because of quantum mechanics. But at the same time, it is also very strange. So Feynman, Richard Feynman, one of the greatest physicists of all time, won the Nobel Prize for his work on quantum electrodynamics. I think it was in 1965. He had this great quote, right, that nobody understands quantum mechanics. And there is a lot of merit to it. Because the problem is this concept of observables, right? So quantum mechanics doesn't provide an objective description of reality. It only tells us, if we look and observe quantum objects, this is what they are going to do. But it doesn't tell us what happens in between, right? And that is free for us to interpret. More formally, we would say that it lacks ontological character, right? It's more sort of philosophical point of view. And again, Niels Bohr, he's the most quotable physicist of all time. He said that there is no quantum world. There is only an abstract quantum mechanical description. We'll see this in action in a moment. This can be rephrased, like David Mermin rephrased it, shut up and calculate. And this is the position that most physicists have taken over the past 100 years. So it works. It allows us to build all this incredible high-tech stuff, but nobody really understands the meaning behind quantum mechanics. So let's start with superposition. So in order to appreciate superposition, we are going to look at a very simple experimental setup at a device called the beam splitter. Now, as the name suggests, the beam splitter is something that takes a beam of light and splits it into two beams of light, right? So we need a source of light, like a laser. We can shoot it at the beam splitter, and what we are going to get is we are going to get two beams of light that exit the beam splitter, and then they travel, in this case, towards two detectors. Now, lasers are beautiful, right? So we can actually see this with our own eyes. You can see the beam of light and then it gets split, right? So it's all very nicely visualizable if you are in the lab. And light is a form of electromagnetic radiation. This is something that we have known since the 19th century. But light is also made of particles, the quanta of light. And this is something that has been shown for the first time by a gentleman that you might have heard of, Albert Einstein. This was year 1905. When he was explaining the so-called photoelectric effect. Now, interestingly enough, this was actually the work that won him the Nobel Prize. It was not the work that he did on relativity. And so basically what we can do with our laser is we can turn down the intensity of the light so far down that we actually end up emitting individual photons, right? And when individual photons go through the beam splitter, we cannot see them anymore because like a beam of light is really nice, we can see it. Individual photon we cannot see, right? We can only sort of look at the detector and recognize that the detector 1 or detector 2 has registered the arrival of the single photon. But we can try to reason about what the photon would do here in this beam splitter, right? And because there is no such thing as half a photon, then the logical thing to assume is that if I send a single photon through a beam splitter, then it should go one way or the other, right? And when we run this experiment in the lab, we would actually see that over time, half of the photons end up hitting detector 1 and half of the photons end up hitting detector number 2, which is sort of in line with this logical assumption, because some of them should go this way, some of them should go the other way, and then over time, this sort of 50-50 pattern builds up. Now, as it turns out, this is completely wrong. And we'll explain in a moment why. But before we get there, we can actually model this in Q#. We can model this in just about 4 lines of code. And the way we can do this is we can write a Q# operation. So Q# has both functions and operations. And the function is classical, as we would say in the quantum community, which means that it runs on normal CPU. And then the operation requires a quantum processing unit. So it needs to run on quantum hardware. So in this case, we will create an operation. And we will allocate a quantum bit to act as our photon that we are throwing at the beam splitter. So we now have our single quantum bit. And then we need to model the beam splitter somehow. we can do this using the H transformation, which is one of the most fundamental operations that you can do on a quantum computer. We will explain more about H in a second, so for now we don't need to get into this. It's enough to say that this should be good enough to model the beam splitter. And then we need to model the detectors somehow, right? And we do this by performing an observation or a measurement of a qubit, which is, that's why it's called M, so it's a measurement, right? And what we get out of the qubit, a quantum bit, we will get one regular bit, or as we would call it, classical bit. So a 0 or a 1, which we can then map to either detector number 1 or detector number 2. And when we run this code, we should see that in 50% of outcomes, we would get a 0, and in 50% of outcomes, we would get a 1. And this is effectively what happens in the lab with the beam splitter. So let's try to run this. I do have here a Jupyter notebook where I can run my Q-sharp. And in fact, because this is simple enough Q-sharp code, we can entirely simulate it locally. So using a quantum simulator, we don't need to submit this for execution somewhere like into Azure Quantum so that it runs on real quantum hardware. So what I'm going to do, I'm going to run this operation 1,000 times. And as it runs 1,000 times, you can see that in half of the cases, we got a 0, and in half of the cases, we got a 1. So effectively, we have reconstructed this experiment, but now with a few lines of Q-sharp. But now let's have a look at when things will start getting weird. So let's stack two beam splitters one after the other. And now with two beam splitters, what we do is, we start the same, right? We emit a beam of light from our laser. That beam of light will be split into two beams of light, and one beam of light will go, as we would say, along the upper path of the interferometer, and then this device is called the interferometer, by the way. And the other beam of light would be then sent towards or along the lower part of the interferometer. And then instead of capturing them with detectors, we are going to reflect them using mirrors and force them to sort of meet again in the second beam splitter. And now, because we have these two beams of light approaching from two separate directions, what happens in the second beam splitter is that there is no further splitting. But in fact, what happens is that the two beams of light are going to interfere with each other. That's why the device is called interferometer. And they are going to recombine into one beam of light and then exit towards detector number 2 only. And we can explain what is happening here entirely using 19th century physics, because there's nothing quantum that we need to invoke to explain this behavior. Because again, light is electromagnetic radiation, and it behaves like a wave. So when I have a beam of light, it will behave like a wave, and all waves exhibit the same behavior. That is, if two waves meet, and all waves, so waves on the surface of water, sound waves, and so on, they are going to interfere with each other. And this is exactly what happens here. So because of this wave nature of light, light interferes here. These two beams of light will interfere with each other, and instead of splitting further, they recombine. So far, so good. But now what happens when I send here an individual photon through this device, right? And in order to do this, I'm going to annotate this picture, and let's try to reason about what would happen to a single photon. So let's imagine that I send here a single photon and it sort of travels towards this beam splitter. Now, moments ago, we said that since there is no such thing as half a photon, then the logical thing for a photon to do is to take one of the available paths, and then over time, it will sort of average out. So let's follow this train of thought, and let's imagine that the photon went here, and then it gets deflected, and then it travels towards the second beam splitter. And this is where our intuition breaks down, because of course, if the photon hitting the beam splitter should go, sometimes this way, sometimes that way, then of course what we should see is that sometimes it goes here, and sometimes it goes here. But actually, all the photons, individual ones, will ever be recorded in this detector number 2. Right? And so there is no good common sense explanation for what is going on here, but quantum mechanics provides an explanation. However, the problem is that the price is quite steep that we have to pay for this explanation, and that is, it disrupts our understanding of how reality works. So let's let's have a look at what quantum mechanics tells us. It tells us basically this. When the photon approaches the beam splitter, it sees that, oh, there is a beam splitter, right? And I have two paths that I can take. And so what it does, it enters the superposition state of both of these paths, right? And that is, in the mathematics of quantum mechanics, it is easily expressible. But here it's very difficult to express this because there are two paths, and so how do you actually draw a superposition? So the best thing that we can do is we can say the photon goes this way and also this way at the same time, right? And then it approaches the beam splitter from two separate directions. It's the same thing, it is in two different places, if you will. And then what happens is, because it approaches from like two separate angles, if you will, it ends up interfering with itself. And then the same thing happens as happened to our beam of light, and it exits only here, right? So this is the explanation that the mathematics of quantum mechanics provides us, right? So let's close this. And we can actually model this super easily. We can model this by effectively just adding a line of code to our previous code, right? So our photon is modeled using a single quantum bit. Then the beam splitter is the H transformation. And for now, we can extend what we said before. So the H transformation will actually place the qubit into a superposition state. And then we have a second beam splitter, so we do another H, and then we perform a measurement which will give us a 0 or a 1. And that we can then map to either detector number 1 or detector number 2. And if I now run this, so this is the diagram, and if I now run this, I will run it 1,000 times, and what we get is we get 1,000 zeros, right? So this is this interference effect that normally should only happen for waves, but now the interference happens for a single photon. So this was really weird, right? Because the only way to explain what is happening is we have to accept somehow the fact that the photon appears to be in two places at the same time. But of course, it's just a photon, right? So we should be able to outsmart a photon, right? Like I have a brain that's made of many, many quantum objects, and this is just one, and doesn't even have a mass, right? It's a photon. But it gets weirder, because when you try to outsmart the photon, it will outsmart you. And so this is the upgraded experimental setup. Basically, the premise is simple. If the photon is really in two places at the same time, let's just add additional detectors and catch it sort of red-handed, being in two places at once. And these are these brown thingies here, and these are the so-called quantum non-demolition traps, which are foremost detectors. So they would allow us to detect a photon without actually disrupting its path. But it doesn't matter maybe here. So I will now annotate this, and let's see what happens. So if I have a photon and it sort of hits the beam splitter, as we said, it will enter the superposition state now here, right? And then it sort of travels all the way here, and it will recognize that we are trying to trap it, basically. And so what we should be expecting, if the photon is in two places at once, we should detect the photon being in two places, and both of these things should detect the presence of the photon. But as it turns out, always only one of them will detect the presence of the photon, and it will be random. So in 50% of cases, this one will say, here is the photon, and in 50% of cases, this one will say, here is the photon. And so if the photon shows up here, for example, then it means that it was forced out of its superposition state. And now it approaches the beam splitter only here. So what is happening now in the second beam splitter? It doesn't have itself to interfere with anymore. So what will happen here is the same thing that happened in the first beam splitter, namely, it will come back to its favorite superposition state, and it travels in this superposition state towards both detectors. And now what happens in those detectors is exactly the same thing that happened in those quantum non-demolition traps, namely, in 50% of cases, this one will flash, and in 50% of cases, this one will flash. So effectively what happens is that the experimental outcome has changed, right? Because previously we had 100% of photons hitting detector number 2, and now we have 50-50 split. And if you think about this, this is really, really troubling, because the photon behaves differently depending on whether we look or not. And this is sort of in a very strict contrast, I think, to how most of us think about reality, because surely when you close your eyes, things are not different, right? But this is what the mathematics of quantum mechanics tells us. So we can very easily extend our code with the quantum non-demolition traps. Again, it's just an extra line. So we start with a quantum bit. This is our photon. We then let it go through the beam splitter. So this is the H transformation. Actually, there should be a different way of modeling a photon, but this is close enough. But the beam splitter, but this is close enough. So for this demo, it is fine. And then instead of having a second beam splitter straight after the first one, we perform a measurement, right? But this is now a different measurement. So in this case, we don't reset the qubit, but we sort of let it continue. So this is what quantum non-demolition traps effectively do. And this gives us a 0 or a 1, which we then can map to either quantum non-demolition trap 1 or 2. And the rest is the same. And finally, we have basically 2 bits that come out of this, right? And in the first case, the bit represents the quantum non-demolition trap, and the second case, it represents the detector. And the outcome here should be, like, this should be random, and this should be random, right? So basically, we have 2 bits, so we have 4 possible outcomes, and each one is equally probable, right? And I think the lesson here also is that since H creates a superposition here, when we measure something in a superposition state, it will produce a random result, right? And it's the same here. H places the qubit again into a superposition state, and that's why we get here a random result, a 50-50 split. So let's run this. So this is here in the same notebook at the bottom. This is the same code that I had on the slide. And if I now run it 1,000 times, you can see that I get 4 outcomes, right? Because we are returning 2 bits, and they are all equally likely to happen, right? So that is this. So this is superposition. Now, let's have a brief look at what is happening under the hood mathematically, but we'll not spend too much time here because we don't have that much time. But basically, a qubit in a quantum computer, this is what we would call a 2-level quantum system. So this is the simplest quantum system that you can envision, because it is a system that can only be observed to be in one of 2 possible states. And that is why we can use a qubit in a quantum computer to model a photon passing through a beam splitter, because that photon has only 2 paths that it can go, so we can only detect it on one of the 2 paths. That's why it is like it maps nicely. But mathematically, a qubit or a 2-level quantum system is described by a vector. And this vector it only has one constraint that is shown here at the bottom, which already implies that there can be infinitely many possible states for a single qubit or a single 2-level quantum object. But the thing about this, and this is what makes quantum mechanics very counterintuitive, is that we cannot ask a quantum object or a qubit about its values of alpha and beta, right? We can only, like this, we cannot ask an objective question like this. What we have to do is we have to choose what is called an observable. And there are a few of these observables. They are represented by matrices. But for now, we only focus on the first one. And basically, each of those observables defines a pair of vectors that can be observed using that observable. And these symbols here represent those observable states, the observable vectors. And they look a bit odd, but this is just a notation from quantum mechanics. These are called kets. And this is just a shorthand way of writing that this is a vector. And so in the Z observable, the 2 observable vectors are called ket0 and ket1, and nothing else. So in other words, when we choose the Z observable to interact with a quantum object, or do a Z basis measurement, because Z observable, Z basis, these are interchangeable terms, we cannot ask, give me your alpha and beta because I want to see you, but you have to say, I have selected the Z observable to look at you. The Z observable allows me to see the states ket0 and ket1, which of these 2 you are in. And if the qubit or a quantum system is really in one of these 2 states, then it will say, thank you for asking, I'm in this or that one. But if it's not, then we have a problem, right? Because this is something that we can visualize very nicely on a sphere. And by the way, this only visualizes the mathematics. It doesn't visualize the actual reality itself, but the mathematics, right? So these observables, they are basically axes that cut through the sphere. And so the Z observable would sort of cut vertically here. And the 2 observable states are then ket0, which is basically starting from the center pointing to the North Pole, and then starting from the center pointing to the South Pole, that is ket1. And these are the only 2 that we can see using the Z observable. But a qubit can also be in one of the infinitely many possible states, like this red arrow here, for example, right? And this is a superposition state, because mathematically it's a combination of both of these observable states. And so when we have our photon that goes through a beam splitter, it actually enters a superposition that is represented by a red arrow. It would be slightly different than this one, but it is like this red arrow, and we cannot see this red arrow in the Z basis using the Z observable because we can only see ket 0 and ket 1. And so what happens when we try to observe a system that is in a superposition using an observable that has observable states like the ket 0 and ket 1 in this case, and the system undergoes what is called a quantum state collapse. And basically, this arrow moves. It moves to one of the two observable states. So the red arrow would move to either ket 0 or to the ket 1, right? So effectively, reality gets disrupted by the fact of being observed. And this is very counterintuitive, right? Because it actually tells us that when we are not looking or measuring or nobody's interacting with the quantum objects, then they are in this weird fuzzy state of superposition. And only when they are being observed or measured, that's when they become real and acquire certain properties. Now, another problem is that quantum mechanics also doesn't tell us what is a measurement, right? At which point the measurement or the observation actually happens. But mathematically, it's all very elegant at that level. And so this leads to many paradoxes, right? And of course, the most famous paradox is that of the cat of Erwin Schrödinger that was both dead and alive at the same time, right? And so I think most people have heard, because I mean, this is one of the most famous experiments in all of physics, a thought experiment. And so what Schrödinger envisioned is, he called it a diabolical experiment. He envisioned a radioactive atom like polonium that is going to decay at some point, right? Because of radioactive decay. And that is a quantum phenomenon. So this is something, that decay process, we can describe it using effectively the equations of quantum mechanics. And so that immediately tells us that if nobody is observing this atom, that it will be in a superposition of both decaying and not decaying, right? And you can see where this goes, because Schrödinger then envisioned, okay, let's put a Geiger counter there. So when the Geiger counter records the decay, it will then release a poison from some sort of a flask, and that poison will go into a box, and there is a cat in this box, right? And so if we now unwind back, right, then if nobody's really observing the system, then the atom is really in the state of superposition of both decay and not decay, which means the Geiger counter has both clicked and not clicked, and the poison has been released and not released simultaneously, and that means the cat is both dead and alive at the same time, until a measurement or an observation of the system happens. And we can actually model this in Q-sharp. So let's start with just the atom, right? So this is our polonium atom. I mean, we can model it exactly the same way as we model the photon in a beam splitter, because in this case there are only two possible outcomes: a decay or no decay, right? So we can map it very nicely to a qubit, a quantum bit. We will then place it in a superposition, but we will not use the H transformation, which creates actually what is called a uniform superposition, so a 50-50 outcome. In this case, we do, it's called a rotation, but I mean, this is just a trick. So effectively what it does, it creates a superposition that is not 50-50, but like 90% and then 10%. So 90% likely the collapse is 90% likely to be to the state ket 0, and then 10% likely to be to the state ket 1, right? And then we perform a measurement, which is the same as we were doing before. So if I now run this 1,000 times, you can see that we have 900 zeros and then 100 ones. So in 900 cases, the atom has not decayed, and then in 100 cases, it has decayed. So let's now connect a cat to this. So this is now, we are stretching this a little bit. So an atom is a single qubit in our model, right? So a cat is a bit bigger, so we will model the cat with 2 qubits, which is like the front of the cat and the back of the cat. Now we just have to make sure that when it dies, we kill both sides of the cat. And so what we do, so this piece of code is the same as before. Now we have to intertwine the fate of the cat with the fate of an atom. And we do this by applying this C0 operation. And the C0 operation in a quantum computer, it is a form of a copy, but it's a bit more limited than that, because what C0 does, it basically looks at the source, which is the atom, And if the atom is known to have become a state ket1, then it will copy the state into the ket, if you will. In all the other cases, nothing happens, right? And the default state of all the qubits is ket0, right? So our atom by default has not decayed yet. And then the ket is in a state ket0, which just means it leaves, right? But as soon as the atom becomes ket1, because of this C0, that ket1 will be copied into the ket, and effectively the ket dies. And so if I now run this, you'd see that we have 3 qubits, right? So we should have 8 possible outcomes here, because we could extract 8 combinations of the 3 bits. But we actually ever see, if I run it 1,000 times, only 2 outcomes, right? Because we either get 3 zeros or 3 ones, right? So if the atom has not decayed, then the ket leaves. And if the atom decayed, then the ket dies. And the paradox, of course, that Schrödinger was referring to is if this measurement goes away, right? What has happened here is this C0 effectively doesn't know what to do. So the superposition of the atom has infected the ket, if you will. It has spilled into the ket, and it's basically waiting to be resolved until somebody performs an observation so that the state of an atom is known. And this is what is called an entanglement. And we are going to talk about entanglement later on, so for now we don't need to dive much deeper. But it is basically that, right? Now, what is the resolution for this paradox? I mean, there is a resolution, although it's not super satisfactory, but it is the best that we can come up with at this point. And that is this. So, in principle, the paradox is like correct, is mathematically correct. But the ket and the atom, they do not exist in a vacuum at like a temperature near to absolute 0, and they are completely isolated from anything, right? Because actually the whole thing, the whole experiment is embedded in some sort of an environment that is made of many, many, many quantum objects, right? There's the Geiger counter that is made of many quantum objects. There's the poison that is made of many quantum objects. There's the box that is made of many quantum objects. There's air in the room, and that's all quantum objects, and so on, right? And because of that, there are sort of quantum parts of this experiment that we don't control anymore, right? And we can actually model this and see what happens. So I'm going to take the code that I already had, and I'm going to throw in this piece here, which is basically just 5 more random qubits that are going to represent our environment, right? And what we do here is we entangle those environment qubits with our experimental setup as well, because these objects interact with each other all the time, and they become entangled as well. And then there's this process that we call decoherence. So basically, in principle, a quantum system maintains its superposition state only for as long as it maintains its quantum coherence. And in this case, because the experiment that we have, so the ket and the atom, becomes entangled with many atoms from the environment, that quantum coherence is very quickly lost. Because of course, those atoms become, those quantum objects become entangled with our experimental setup, and the measurement of those is outside of our control because they are not part of the experiment, right? And effectively, the outcome is as follows. If I run this, you will see here that now we have 8 qubits in this particular piece of code. So we should have 256 possible outcomes, but actually we only have 2, right? We get 8 zeros or 8 ones. But the problem is only 3 of those are the ones that we control, right? Because that's the ket and the atom, and the rest is environment. And as soon as one of them is like the 5th one, let's say, is known to be 0, we know that these other ones will be 0 as well, and the coherence of the quantum superposition is lost. So, long story short, it really means that fundamentally the thought experiment was correct. But the problem is that this coherent quantum superposition that spans all these quantum objects would last only a fraction of a second. And this is the explanation that we have at the moment. And this is actually the same effect that makes quantum computers so damn difficult to build. Because in order for us to do quantum computations, we need quantum hardware, right? And that quantum hardware, those are quantum objects, and they need to maintain their quantum coherence. So they have to be absolutely isolated from the surroundings and the environment, right? And that's why many architectures of quantum computers actually use these sort of cryogenic chambers to be cooled down to near absolute zero so that nothing happens, right? And they don't get disrupted. And yet still, they manage to lose their quantum coherence very, very quickly, right? So this is the reason why we don't see these quantum superposition effects at the macro scale. Okay, the next thing I want to talk about is the uncertainty principle. And in order to appreciate uncertainty principle, we have to introduce another physical property that's called spin. We don't need to go very deeply into this other than saying that this is something that electrons have. And mathematically, a spin is described by a vector that has components along each of the three axes in the three-dimensional space. So there is a z component of the spin, there is the x component of the spin, and there is the y component of the spin. And in order to actually observe any of these, we have to use an observable that is compatible, right? So for the z component of the spin, we have to use the z observable, and for the other ones, we have to use other observables that we didn't talk about. And each of those observables, as we said earlier, only allows us to see one of two possible states, which is actually very convenient for a spin, because spin can also have only one of two possible states along each axis. So it's like +1, -1, and then it would be like left, right, and so on. And this is basically what we can do with the electron and its spin. This device here is called the Stern-Gerlach apparatus. And it's actually a simplified variant, but it's good enough. And so what we do is we start with the electron, and we can prepare this electron with one of these components here in a certain value, right? So let's take the z component of the spin, and it can only be up or down, right? So let's prepare it with up. And now what we do is we send this electron towards the screen. So this is a screen here. And the electron will go through a magnetic field, and the orientation of magnets is here important because the magnets are stacked now on top of each other. And with such an orientation of magnets, this electron will interact with the magnetic field, and the magnetic field can only deflect the electron up or down. There's just no other way for an electron to go. So effectively, such an orientation of magnets acts as a z observable because it only allows us to see spin up or spin down, right? Which is, I mean, this, by the way, the up and down are just labels, right? Previously, we were calling that ket 0 and then ket 1, and it's really the same thing. But the point is that we have prepared some quantum state, and we are looking at this quantum state using an observable that is compatible. So in this case, 100% of those electrons will be deflected up because we have prepared the z component of the spin to be up. Now we are using the z observable, which can only deflect up or down. So effectively, the observable is asking a question, is your spin up or is your spin down? And then the electrons all go up. And if I do a different thing, and that is I prepare an electron with the z component of the spin to be up, but I use a different observable, which actually is not very nicely visualized here because it's two-dimensional. But previously, the magnets were like this. But we can rotate these magnets to be horizontal. And now the magnets can only deflect left or right. And so now, effectively, we have created an X observable, right? Because the magnets are asking, what is your X component of the spin? Is it ket plus or is it ket minus? Well, it's actually neither, right? Because we prepared the Z observable, or we prepared the Z component of the spin only. And so as the electron goes through this observable, or this pair of magnets, it will be randomly deflected one way or the other because it doesn't know what to do. So it acquires value upon observation. So we can easily model this in Q-sharp, and we'll see in a moment why this is significant. So we will start by allocating a new qubit, and this will be our electron. And the default state of an electron is ket 0, which is like really like ket up, right? Because it's a state that is observable in the z basis, in the z direction. And now I can do a measurement. And so far we were doing all the measurements in the z basis because that's the default for quantum computing. But we can actually parameterize this. And so if I measure in the z basis, then I will get a deterministic result, exactly the same as we had here, right? And if I measure in the x basis, I will get a random result. And so basically this is something that we can parameterize. So I can jump over here to the code, and if I run this 1,000 times, so now you can see here we have started with a state cat 0, so like spin up, and we measure in the z basis, and we get 1,000 results that say cat 0, because we are asking a correct question, right? Because we are asking, is your spin up or down? And it's saying, thank you, it's up. And if I prepare a spin up and then measure in the x basis, so here I'm passing the x basis as parameter, you can see that I get a random result, because that is a wrong question that we are asking, if you will. But here's another thing. We can actually chain these measurements, right? These observations. We can do one after the other. And this is where things get a bit more strange, because if we imagine that we start with an electron with the z component of the spin prepared up, and we send it through this x observable, so magnets oriented like this, then of course we already determined that this is a wrong question that we are asking, and we'll get the random result, half go here, half go here. But instead of terminating at this point, we can then put up a pair of z observables. So now ask a question, okay, thank you for going this way, but now tell me what is your spin in the z direction. And this is something that we initially set to be spin up, and now we should get a deterministic answer that it is spin up, but that's not what the experiment will show, right? So we actually get here a random result as well. And so what this tells us is that this measurement here ended up destroying information that we originally set in the electron. And the way you can think of it is that if you look at a quantum object in a wrong way, you will destroy information, right? And this is actually the foundational principle for quantum cryptography, because it's like security that is built into the very fabric of reality. You encode something into a quantum object, and you have one shot to read it. And if you do it wrongly, then you will destroy this information, right? And so we can very easily model this in Q#. We start by our qubit, so this is our electron, and then we measure this qubit using first the x observable, which is incompatible, right? Because we start with the state cat 0 here, so that's already incompatible. And then we measure in the z basis, and here instead of getting 100% zeros, we will now get a 50-50 split. So I can go down here and run this. Oops. And if I run this 1,000 times, you'd see that the outcome is really random, right? And if I just comment out this initial measurement in the x basis, right, then what's going to happen is that this randomness is going to disappear, right? And now I'm back to a deterministic result. So this is the uncertainty principle. And effectively what uncertainty principle tells us is a fundamental thing in quantum mechanics, that there exist pairs of what we would call them conjugate variables, and we just cannot know them at the same time with arbitrary precision. So we cannot know the z component of the spin and the x component of the spin at the same time. We just cannot know them. We can know either one or the other. Like, it's not that one replaces the other, right? They are both there, but we cannot know them at the same time. And so in this case, the measurement using the z observable creates maximum uncertainty for the measurement in the x observable and vice versa, right? So again, looking at the object wrongly will destroy information. And so Einstein hated it, right? He said God does not play dice. But actually, this is at the heart of quantum mechanics. So when Heisenberg developed this for the first time in 1927, he did this for position and momentum. So there is an uncertainty relation between position and momentum. So actually, at the quantum level, we either know where the quantum object is, but we don't know how it is moving, or we know how it is moving, but then we don't know where it is. I mean, it's the same principle as these two components of the spin. And even more dramatically, there is an uncertainty relation between energy and time. And this is one of the most mind-boggling things that are out there, I think, in all of science. Because in order to appreciate this, let's imagine an empty container. And then we remove everything out of this container. So all the air molecules and all the dust and all the bacteria and what have you. So what we end up with is a vacuum, right? Emptiness. And now, if I ask you what is happening in the vacuum, then you say nothing, because there's the definition of it. If I would ask you what is the energy in the vacuum, then you say 0, because that's how it should be. And that is partly true, but only on average. Because as it turns out, if you take a tiny, tiny slice of time, right? Now you have such an unbelievably precise knowledge of time, then because of the uncertainty between time and energy, very weird things can happen. And these are the so-called quantum fluctuations that are visualized here. So as it turns out, at these tiny time intervals, you have such a precise knowledge of time, you lose all the confidence in the energy. And the so-called virtual particles appear out of nothing. They just come to existence. So it's like a God moment of creation, right? Like something out of nothing. And what they do is they immediately annihilate themselves. And by annihilating themselves, they release energy. And this is the energy that they used to create themselves in the first place. So they effectively borrowed the energy from the future. And this is actually happening all the time, everywhere. It's like teeming with activity. And for a long time, people thought that this is just a mathematical trick, it's just a consequence of mathematics, it's just a trick. But it turns out we can detect this effect in a vacuum. There is something called the Casimir effect that allows us to, or that is actually detectable experimentally, so we know that it is really happening. Okay, let's close off with entanglement, which is actually the weirdest of all. And so in order to appreciate entanglement, we need Stern-Gerlach apparatus again, but actually we need 2 of them now. And we start with a source of electrons, but now we are going to be emitting not 1, but 2 of them. And they will be entangled. And effectively, this means quantum mechanically that they interacted with each other, or they were created using the same event. And we send one of them over there and one of them over there, and there is a Stern-Gerlach apparatus, and there is another one. And they don't have a known spin at this point, right? Actually, what they have is they are actually in a superposition state when it comes to the spin direction. So as they travel towards the Stern-Gerlach apparatus on each side, what will happen is that we are measuring them using the Z observable, so we are asking, is your spin up or is your spin down? But because they are in a superposition state, we already know that they will only make a decision when they are asked. And at some point, they reach here, and then they are asked, so they say, my spin is up or my spin is down, it will be 50% probability. But the thing about these entangled electrons is that they are going to respond randomly, so it's like effectively like a quantum coin toss, but they'll be perfectly correlated with each other. So when one says up, the other will say the same thing, and so on. And so now, what we can do is, okay, we can ask ourselves what is going on here. So how do they signal themselves? How do they align on the value that they are supposed to be choosing, right? So we can actually spread these 2 apparatuses very far apart. And this experiment was done by putting them like kilometers apart, right? And now, what you can do, you can time the measurements very, very precisely. And because they are far apart from each other, you know that no information can travel between them, because not even light has enough time to sort of jump between them and you know, reach one and from the other as we are measuring them. And we of course know that speed of light is the universal speed limit. Nothing can travel faster than light. And yet they still maintain this correlation, right? So it's random, but it's perfectly correlated. So we can very easily do this in Q#. We already did this actually when we were trying to kill the cat. So we allocate 2 qubits and we place the first qubit in the superposition state, right? And then we do the C0. So we say, if you become cat 1, I want to also be cat 1, otherwise I will stay cat 0. And effectively, mathematically, what happens here is that the superposition infects the other qubit, and they are now in this entangled state, right? And they will remain in this entangled state until they are measured. And so then they can be measured, and as long as we measure them in the same basis, so when they are both measured in a Z basis or both in the X basis, they will produce a random result, but it will be perfectly correlated. And this is what we can then return. So I will run this code. And so here we have an entangled pair, and you can see it produces 2 zeros or 2 ones always, right? So it's like random, but perfectly correlated. And if I measure in the X basis, then I will get 2 pluses or 2 minuses, so again, perfect correlation, so 2 lefts, 2 rights. So it's all working as expected, or maybe as unexpected. This is entanglement, right? So now, what is going on here? So there are 2 possible explanations, right? One is sort of logical and intuitive, and the other is absurd, and you can guess which one is correct. So the first one, that's the one championed by Albert Einstein, out of all people. We could assume that the electrons just pre-agree on how to respond to measurements, like 2 conspiring criminals, right? Like we say, if we are asked about the z direction, let's say up. If we are asked about the x direction, let's say cat plus, right? So they just pre-agree on all the possible directions, because can be many. And then there is really no mysterious signaling and what have you, right? It's just they pre-agreed and then they stick to their story. And then the other option is that they are entangled, like quantum mechanics tells us. They produce the experimental outcome randomly at the moment they are measured, and they become instantly correlated. But of course, nothing can violate the speed of light. So actually, there's nothing traveling between them. There's no signal, but they become instantly correlated. So it's like saying it's magic, basically. Einstein called it spooky action at a distance. Now, now, for a long time, it seemed this is just a theoretical argument. It's just like, okay, it's a discussion, right? Who cares? But in 1964, at CERN in Geneva, John Bell came up with this brilliant theoretical solution to this that allows us to actually determine which of these 2 explanations is correct. This is the so-called Bell's theorem, or Bell's inequality. And so what he realized is that the predictions of these 2 approaches would actually not be the same. Because when we measure in the same basis both of these entangled electrons, we measure them in the same basis, then it means that the angle between those measurement bases is 0, right? Because it's the same. And then the correlation is 100%, so we are here at the top of this chart. But then if we measure one of them in the z basis and one of them in the x basis, we have a 90-degree angle between them, and the correlation drops to 0. So we are at the bottom here, right? So if they actually, the thing is we can measure at any angle, because we can rotate these magnets however we want. And if we measure on one side in a z basis and then we rotate the other only slightly, we can measure it, for example, a 45-degree difference between the 2 bases, right? And in such a case, if they pre-agreed on how to respond to measurements, then this correlation actually drops linearly. But quantum mechanics predicts that it would not drop linearly. They would actually follow a cosine of the angle between them. So actually at the 45-degree angle difference between the measurement bases, the correlation is actually stronger than what we would see here. It's about 71%. And now all is needed to be done is just to set up an experiment that confirms this, which is actually surprisingly difficult. But so it took a long time. But over decades, these 3 gentlemen, Alan Aspect, John Clauser, and Anton Zeilinger, they actually set up a series of experiments that exactly confirm this, and this blue line here, that basically the correlations that are exhibited by these quantum objects are stronger than anything that they could possibly pre-agree on. So mathematically, what does it mean? Well, it's actually surprisingly simple. So if you take a single qubit, a single quantum object, a 2-level quantum object, we already said it's described by a 2-dimensional vector. Now quantum mechanics says that if we have a pair of them, right, then the system consisting of both of them is now described by a tensor product between them. And the tensor product between 2 2-dimensional vectors creates a single 4-dimensional vector. And as long as they are not entangled, you can always write it like this, calculate the 4-dimensional representation, and go back and decompose back into this representation. But once you have an entangled state, you have a 4-dimensional representation, but you cannot go back to the 2-dimensional vectors, right? It's like a trapdoor function. So the 2 objects exist, and once they become entangled, they only have this 4-dimensional representation, and there is no more individual representation of those objects according to the mathematics of quantum mechanics, right? And so this is very troubling because we can take one of these objects and we can send it there and we can send the other one there. But now quantum mechanics tells us that actually the smallest possible unit of reality is this entangled state that spans both of them, right? And so they effectively do not exist as independent entities in reality anymore, and yet we can spatially separate them. And this is why it appears that this is not compatible with our understanding of space and time. And we call this non-locality. And again, this is something that we know for sure it's there because it's been experimentally confirmed, and the Bell's theorem was confirmed experimentally. So Henry Stapp called it the most profound discovery of science because it really tells us that the quantum world is very weird. Now we cannot use this for faster than light communication, but we can use it for other interesting things. And entanglement is now a key aspect that is being explored in quantum computers for any potential computational advantage. There are quite a few interesting protocols that are built on top of entanglement, like this one here, and it's called teleportation, right? I mean, it's already the name. So the way it works is that Alice and Bob start by entangling a pair of qubits. And at this point, they can go their separate ways. And then Alice takes her qubit, and she creates another qubit as well, which is denoted here as M. And she places that M qubit in any state she wants. So she gives it any alpha and beta that she wants, right? So it's now in some sort of a quantum state that is known to her only. And she then performs what is called a joint measurement over both of them. And the measurement of two qubits produces 2 bits, right? So she gets, effectively a number between 0 and 3, if you will. And she takes those 2 bits of information and she conveys that to Bob over any communication channel that they might have. This can be over the internet, it can be over phone, over smoke signal, doesn't matter, right? It's just a classical way of exchanging 2 bits of information. And then Bob takes these 2 bits of information, which again is a number between 0 and 3, and the teleportation protocol prescribes, depending of this value, to apply a certain transformation to his part of the originally entangled pair. And as soon as he does that, that qubit that is in his possession will sort of automagically morph into the state that originally was in Alice's possession, right? Now, remember, it's not that these 2 bits of information carried somehow the instructions on how to reconstruct this M state, because that is alpha over beta. These are complex numbers, so you need actually a lot of memory to represent this, right? So it's impossible to encode this M state into those 2 bits of information. So this is like a facilitator, if you will. And basically this guarantees that that protocol cannot be used for faster than light communication because it's actually limited by these 2 bits. But as soon as that happens, as those 2 bits are known, then Bob is able to actually recreate that M state on his side. And that M state was actually destroyed upon measurement because that caused the quantum state collapse. So Alice doesn't have it anymore, and it sort of appears on this side, right? And there is no quantum communication channel between Alice and Bob. So it's not like it was transferred in some way. For all intents and purposes, we can think of it as it ceased to exist here and reappeared here, but actually nothing traversed the space and time between Alice and Bob. And we can actually run this in Q#. So I have this protocol implemented. It's in process, right, with like 2 actors. So we'll not go through this code because it's a bit too much, but we can run it, and I will run it 1,000 times, and it basically just keeps track of the success rate. So that actually worked. So if you'd like to look at this later on, then there is a link to the demos, and actually this is everything. There you go.